I'd like to begin by acknowledging my collaborator, Mina Yang. She's a student who graduated with me this summer and is currently at a postdoc at NYU. So jumping right in, Ensemble Forecast is a crucial part of ensemble data assimilation, but for high resolution or coupled models, it can be prohibitively expensive. One way to reduce the cost or to avoid the cost of an ensemble forecast in data assimilation is to use ensemble optimal interpolation. So in ENOI, you have an ensemble, but the perturbations from the mean are time independent. Only the mean evolves in time. You evolve the mean in time using a single physics-based forecast. Obviously, this has a lot less computational cost, but on the other hand, your ensemble is much less representative of the errors of the day than in something like an ENKF. There's also quite a bit of interest in developing data-driven forecast models where you replace the physics-based forecast with something data-driven because the data-driven forecasts are usually a lot cheaper. This is a really interesting area. I think the challenge at this point is in getting a data-driven forecast that is accurate enough to be worth using. A classical approach to data-driven forecasting is to use analogs. The way that analog forecasting works is you start with a library of states catalog drawn from, for example, a reanalysis or a hindcast. And to make the forecast, you take your current model state, find the nearest neighbor in the catalog, and then use the next state in the catalog as your forecast. We are not going to do analog forecasting. Even though analog is in the title of the talk and the titles of the papers, we do not do analog forecasting. In fact, we're not doing any kind of data-driven forecasting. What we're going to do is have an analog ensemble, but we will make one physics-based forecast, or small number, but for the sake of presentation, assume just one physics-based forecast. And then you find n nearest neighbors in your catalog, and you use those as your ensemble. Now, you do want to recenter your ensemble so that the mean of the ensemble is equal to your single physics-based forecast. And you do probably want to rescale the spread of the ensemble to make it have a value that's more reflective of forecast error, as opposed to just being reflective of how close are the n nearest neighbors in your catalog. But broadly similar, it's very similar to ENOI in the sense that you only make one physics-based forecast. Here's an illustration. So I've pulled out sea surface temperature, a subset of the domain, for a QG model, double gyre. At the left edge, you've got a Gulf Stream that separates from the boundary, and there's an SST front associated with that. So in the bottom left, you can see SST, and you can see the front where it separates. And that location where it's separating is at a fairly low latitude. In the bottom right, you see a different model state where the separation and the SST front are at a much more northern latitude. In the top center, we have the SST forecast error standard deviation that you would get from climatology. So this is what you would have in an ENOI, for example. And climatologically, the separation point for this front wanders around quite a bit. So you have a broad region with lots of variance, and you don't really see any meanders of the jet because the meanders climatologically sort of cancel each other out. To the left, we have the same thing, forecast error standard deviation, that you would get from an analog ensemble of analogs of this state on the bottom left. And you can see clearly that there is, that the forecast error standard deviation knows about the separation point. It knows about the latitude here. It also knows about the meanders of the jet. It's basically just a much more realistic representation of the forecast error. Similarly, on the right, we have the analog forecast error standard deviation associated with the state on the bottom right, and it's much more localized. You have a much sharper region of variance, and you can also see that the meanders of the jet are much more realistic than in the ENOI case. That's just to illustrate what replacing a climatological ensemble by an analog ensemble does to the forecast error covariance matrix, specifically just the variance. All right, analogs have a lot of uses. I mentioned analog forecasting. You can also do downscaling and lots of other stuff. There's a big literature. One of the things that's common to do in that literature is to construct analogs. So instead of just finding an analog from your library, you take some analogs from your library and then you put them together in a special way and get a new constructed analog. So we're going to talk about a way of doing constructed analogs that's new using what are called autoencoders. Autoencoders are a machine learning approach. It's a neural network architecture with two pieces. So first you have an encoder. It takes the model state and it encodes it into the latent space. So Z is the encoded model state. Then you have a decoder, which takes this encoded latent space vector Z and reproduces the model state. And you train the autoencoder, which consists of both the encoder and the decoder, you train it to try to get as close as possible to an exact reconstruction. So you want X hat, the output, to be very close to X, the input. How can you use this to generate analogs? So first you take your physics-based forecast, the one forecast that you made, you encode it into the latent space. Then you add noise in latent space. You generate an ensemble in latent space, and then you decode it back to the full state space. And you have now an ensemble of states that are similar to the one that you put in as an input. If the decoder was a linear function, then the covariance that you would get by doing this analog ensemble would actually not change in time. It wouldn't vary in response to the variation of your single forecast. So the fact that the decoder is nonlinear is what allows the covariance to change as the forecast itself changes. The data assimilation method that we build on top of these constructed analogs, we're going to call constructed analog optimal interpolation. So we're going to test these methods in a multi-scale Lorentz 96 model. And here, to give you a sense of what this model is like, there's a Hofmahler. Horizontal axis is time, vertical axis is the state vector. And you can see that there's some sort of large scale waves that sort of nonlinearly propagate and interact. And that is basically your standard Lorentz 96 dynamics. You can also see that there's these streaky sort of noise things superimposed on top. We have connected the large scale Lorentz 96 to a small scale. And it's sort of like, but different from the two scale model that you might be familiar with. A little bit more background. So here's an energy spectrum for this model. The blue line is the climatological energy spectrum. Everything to the left of the dashed line is just regular old Lorentz 96. Everything to the right is the small scales that we coupled it to. You can see for the small scales, there's a peak small scale instability over here, maybe a harmonic down here. The solid line is, the solid black line is going to be the Nyquist wave number for the observing system that we're going to use on our data assimilation experiments. So we've set it up to be a difficult test where the observations are not able to actually resolve this small scale peak instability. Our setup is going to be a one-day forecast, 0.2 model time units. Observation error standard deviation, 1 over the square root of 2, about 0.7. Ensemble size is 100. We do have multiplicative inflation and localization, which are both tuned independently to get optimal performance for each method. I'm just going to quickly tell you about the analysis RMSE for this. So our ENKF, our baseline, in a sense, is actually a serial square root assimilation, and we get an RMSE of 1.35. So the observation error is about 0.7. So we're doing about a factor of 2 worse than the observation error. But this is a difficult test because of the long time window and the sparsity of the observations. If you then compare to just plain ENOI, RMSE is 2.27, which is significantly worse than the ENKF. Of course, you expect that. It's much cheaper. It's a factor of 100 cheaper for an ensemble size of 100. And 2.27 is actually still pretty good for this model. The climatological variance is still much larger than that. So whether this is good enough, depends on your needs, but it's still sort of doing a decent job. If you then take the climatological ensemble and you replace it by analogs, you get an RMSE of 2, basically. So the RMSE improves by about 15% for this model, which is an important and a valuable improvement, but not world-shaking. If you then replace the found analogs that you find in the library with constructed analogs that you construct using an autoencoder, the RMSE goes down to 1.30. That looks like it's better than the square root filter, but to be fair, the difference between these is not statistically significant. So I think the correct interpretation is that this constructed analog method in this particular problem does as well as the ENKF. And it's about 100 times cheaper because making the analogs using the autoencoder is extremely cheap compared to making the forecast. All right, if you have a high resolution or a coupled model, which means that an ensemble forecast may be prohibitively expensive and you might want to use this kind of a method instead, then you're not going to be able to train an autoencoder to reproduce the whole model state. It's just too big. Autoencoders can't handle something with 1 billion variables. You have to do something else. So what we're going to propose is to cut the domain up into patches and train your autoencoder to only reproduce local patches. Now, if you're using an LETKF, for example, that's perfect, because in an LETKF, you only deal with one patch at a time. Not everybody uses LETKF, though, so we're going to next present a way to construct an ensemble of global model states using patches. This basically makes the training easier and brings the cost down and makes it practical. So in this figure, I've got 4 panels. Each panel is a different ensemble member. It's a different analog. If we were trying to just do a reconstruction, then all the ensemble members would be the same, and they would all be very close to the gray line, which is the true state that we're trying to make analogs of. But we've deliberately sort of made the analogs a bit different so you can see the differences. The different colors correspond to different patches. And the crucial thing to notice here is that the boundaries between the patches are different from one ensemble member to the next. So the boundary between orange and green is here for ensemble member 1. For ensemble member 2, it's in a different place. That is crucial to getting good performance in your patched analog ensemble covariance matrix. If you didn't do that, then the location of one patch would just be completely independent of the location of another patch. So an observation in one patch would not be able to update the variable across patch boundaries. So it's important to have patch boundaries moving from one ensemble member to the next. We do some analysis of this. We show that moving the patch boundaries like this is like localization, where the localization radius is equal to the size of the patch. So as you might expect, the performance degrades for very small patch sizes. It's like using a localization that's way too tight. Similarly, performance degrades if you make your patch size really big, just because it's harder to train an autoencoder to do a good job on a really big patch. Putting these things into the same data assimilation setup for multi-scale Lorentz 96 as before, we actually found that this constructed analog method with patches outperforms the ENKF. We get an RMSE of 0.9, whereas previously for ENKF it was 1.35. All right, there's many other things to say about this, which I don't have time to, but if you're interested, I urge you to take a look at these 2 papers, which have a much more in-depth discussion.